Okay, let's start class. Today we will talk about chapter 6. So I've just posted chapter 6 slides and also the exercises, problems from the textbooks in the Moodle. So you can download the slides and also check for the exercises. As I said, we don't have any homeworks. So we only have 4 homeworks. But the exercises that I posted, you can just work on these exercises as a practice problems and to prepare for the exam too. Okay, so here, this is the tentative schedule. So we've already start. So we are on schedule. So today we will talk about chapter 6, and Wednesday we will finish that. For the next week, we will talk about chapter 7. Okay, then the week after next, we will have the spring break. Right after the spring break, we were going to have the exam 2. Exam 2 will be just like exam 1. So I would recommend you to start to prepare for the exam 2. And I will post it an old exam for the exam 2 later this week. Okay. And but the form, but the type of questions will be very similar to the exam 1. So I will have some multiple choice, true and false, and also some problem with several parts, and you need some calculations to and write some things, so just like exam 1. And exam 2 covers the chapter 4, 5, and 6. Okay, although we will talk about chapter 7 before the exam 2, but I will leave the chapter 7 to the final exam. Okay, and after the midterm 2, we will have the Bayesians, 3 lectures on the Bayesians. Okay? And Dr. Guo, she will talk about the Bayesian categorical data analysis. And after that, we will have the model for matched pair. That's the chapter 8. And then we will have the presentations. So I will talk about more details probably on Wednesday, this Wednesday. Okay, so I will ask each of you to work on a final project. You can use the data set, and I will talk more details. Okay, so if you have any questions, that's just leave it to Wednesday, so you have enough time to prepare for that. So you can use the exercises, data sets from the textbook, or you can use the data sets from research, and but it should be as a categorical data analysis, and you should use at least one of the method from the method that we talk about this semester. But if you want to use some other method outside this class, that's totally fine. Okay, and I will ask you to present in the last 3 lectures. So each lecture we will have 3 or 4 of you to do the presentations, and I will talk about more details later. Okay. Yeah. Oh, of course, I will provide the solution for the old exam. Okay. So that's the schedule for 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 the rest of the semesters. And the final exam, yeah, make sure you have no time conflict for the final exam. Okay, so exam 2, final exam, they will just like exam 1 will be in person. Okay. Okay. Any questions? Okay, let's talk about chapter 6. So chapter 6, as I said, the slides exercises are already in the Moodle, so you can download it. Chapter 6 is the multi-category Logit model. It's an extension, natural extension for the logistic regression models. For the case that we have more than 2 categories for the response variable. Okay, so if we have more than 2 categories, then we have 2 types. If we just have 2 categories, it doesn't matter. Logistic regression always applies. Okay, but for the more than 2 types, so there were more than 2 categories for the response. Then we have 2 types of problems, 2 types of response. One type is it is nominal response. So nominal means that there is no order structures in the response. So all the categories has no ordering relationships. So that's uh, that's one type we will talk about. And another type is the response is ordinal. It is still a categorical variable, but it has some order relationships among these categories. Okay, so we will talk about both in the multi-category Logit model. And you may ask why we don't have that in 2 class. If 2 class, if there's an order, it doesn't matter. It's 0, 1. We always model that 0, 1, right? So this only happens when we have more than 2 class in the response. Okay. So the outline for chapter 6 is we will generalize the logistic regression to the multi-category response with 3 or more categories. As I said, 2 types of response, nominal response as unordered and ordinal response as ordered category. But for the explanatory variable, it can be quantitative, categorical, or both. Okay, so the model assumes that the counts in Y follows a multinomial distribution. Remember multinomial? So multinomial distribution is a extension of the binomial, right? So we have more than 2 classes, okay? And the multi-category generalization of so it's the binomial distribution. So we will talk about 4 types of models in chapter 6. And today we will talk about 2. And on Wednesday, we will talk about the rest 2. Okay, so the baseline category Logit model for the nominal response, and then we'll talk about the cumulative Logit model for the ordinal response. On Wednesday, we will talk about the cumulative link models for the model checkings and extension for the cumulative link model. And also, we will talk about the pair category Logit models for the ordinal response. Okay, so this is the outline for chapter 6. So first, let's talk about the baseline category Logit model for the nominal response. Okay, you can see now for this type, we only consider the unordered response variables. And by its name, you can see that we have a baseline group. Okay, so we use the baseline group and all the other groups compare with the baseline. Okay, so let's have the C as the number of categories of the response. Okay, so the response probability, then we have the pi 1 through pi c. Okay, so this is so these are the probability of having the y equals to 1, 2, or 2 up to the c categories. And of course, if you add them together, you will have 1, right? So we have different ways to set the baseline. Okay, we can choose the first category as the baseline. We can choose the last one, or we can choose a specific one. Not the first, not the last, somewhere in the middle. So they are all fine. But here, let's just say we treat the last category as the baseline. Okay, and all these, it's almost the same if you choose a different baseline, like choose the first. Okay, so if you know the interpretations and finding the probabilities, do the inference for using the last category as the baseline, you should be able to know if we choose other group, other category as the baseline. Okay, so here we just set the last category C as the baseline. So the baseline category Logit model with just one explanatory variable X is this one, right? So it's the log odds, okay? Just like logistic regression, is equal to alpha j plus beta jx. And here the j ranges from 1 through c minus 1. Why it's just to the c minus 1? Because we use the last group as the baseline group. If we include the c here, then it's nonsense, because the pi c over c, that's 1. That's always 0. So what does that mean? That means if we include the c here, you can easily see the log what? Log 1. So log 1 is what? Log 1 is 0, equals to that. So in other words, the alpha c is equals to what? Always equals to 0. And the beta c is always equals to 0. So that's the baseline group. So for the baseline group, we don't have the alpha beta because they are both 0. Okay? So that's why we only stopped at c minus 1. So the model has how many equations? We will just have c minus 1 equations. Is that right? So you can see that's the, if let's say we have 3 categories, then we will have 2 equations. The first one is the log odds between category 1 and category 3, right? It's the alpha 1 plus beta 1 x. And the equation 2 is what? Is the log odds between type category 2 and category 3 equals to the alpha 2 plus beta 2x, right? Then how do we get the log odds for the category 1 and 2? We can still get that. That is just the difference between the equation 1 and equation 2. Is that right? Because if you take the difference, you will see the category 3 cancels out. So it becomes the log odds between category 1 and 2 is equals to the difference between the equation 1 and equation 2, which is what? Which is the difference of alpha 1 and alpha 2 as the intercept, and the difference for the beta 1 and beta 2 as the slope. Okay, so you can easily find this relationship. So for the baseline group, as I said, the alpha and the beta, they are both equals to 0. Okay, and here, this is only for the 1 predictors, right? And you may ask, what about more than 1? That's the same. It's just add some more explanatory variables. And the way that we have the equations are the same, just with some additional x variables. Is that right? And also the way we calculate the log odds between the pi 1 and between the category 1 and 2 are the same. Okay, use the difference for the intercept as the new intercept and the difference of the slope as the new slope. Okay, between the two non-baseline categories. Okay, and for the softwares, for the multi-category Logit models, they will fit all C-1 equations simultaneously. Okay, so it will just do that at once. So let's see an example. So this is the what do alligators eat example. So here in this data set, we have 59 alligators captured in Lake George in Florida. So the response variable is the food choice, the primary food choice that we found in alligator stomach. Okay, so we have three types. The first type is the fish, second type is the invertebrate, and third is the others. And do we have an order here in the response? No, we don't, right? Fish, invertebrate, and the other, we don't have an ordering relationships in these three groups. Okay, so we can just treat the y as nominal, right? And for the explanatory variable, we use the alligator length. Why use the alligator length? Because the alligator length is a proxy for the age of the alligator, right? The size should be isn't is provides the similar information as the age. If the age uh, of the alligator is older, of course the size will be bigger. So we will see if the size or the age will change the food choice for the alligators. So that's the uh, motivation for this study. And data set is available here. If you use this link, you can download the data set. And then, so in this data set, we have two variables, 59 observations. The first variable is the length, and the second variable is the food choice, primary food choice. Okay, so here for the multi-category Logit models, we can use the VGAM model library. Okay, so this is the package for the multivariate GLMs. So multivariate GLM means that we have multiple response variables, which is exactly the case here. Okay, such as the like here the multinomial models. So the main function in this package is the VGLM. Okay, so we have the response is Y, that's the primary food choice, and use the length as the predictors. The family is multinomial, right? And the data set, okay? So here for the, so for the coefficient, we fitted the model and I output the coefficient using the matrix form. That is actually a good way to show what is what. Okay, so here you can see we have two rows. The first row is the intercept. The second row is the coefficient for the length. Okay, if we have more than two x variables, then we will have some additional rows. But for the columns, we have two columns because we have three types, right? So we have the log odds for the category 1 and 3, and the category 2 and 3. Because the last group, the third category, is treated as a baseline group. Okay, so you can see the intercept for the model the log odds between the fish and others, because the fish is the type 1. Okay, fish is the category 1, and type 3 is the others. Okay, as the intercept is 1.6, and the slope is 5.7. Okay, I'm sorry, no, slope is negative 0.11. Okay, so that's for the log odds between the fish and others. For the invertebrates against others, the log odds model has the intercept is 5.7 as the intercept and negative 2.4 as the slope for the length. Okay, and for the summary of the models, you can see this one. So it provides the similar information on the estimated values, but of course the summary gives more. It also gives the standard error of each coefficient with the z values and the corresponding p values. And these p values are based on these z values, which is called word test. Remember that? Word test. Okay? So based on the model outputs, we can write out three equations, right? Because we have three classes. The first is the category 1, that's the fish, versus the other. So we have the log odds model with the intercept and slope, right? And the invertebrates against the others. We have this. So these two equations, we have the coefficients and the intercept directly from here, right? But the third one, the log odds between the fish and invertebrate, that is derived from the difference of the intercept and slope from the previous two models. Okay, so in other words, here the negative 4.08 is from where? Because that's the 1 against 2. Is that right? So it should be using the intercept for the 1, for the category 1, that's 1.62 minus what? Minus category 2's intercept, that's 5.7. Okay, and that gives the negative 4.08. That's how we get the intercept. Okay, but for the slope, same thing. Using this as a slope, so it's the negative 0.11 minus what? Minus this one. Okay, minus negative 2.465. All right? But we have minus negative, so that becomes plus. So that's why the the slope is positive for the log odds model between the fish and invertebrate. Okay, so that's how we get these intercept and slope. So make sure you know how to find that. Okay, so interpretation, how do we interpret the results? It's exactly the same as for the logistic regressions. Okay, so we can interpret based on using the odds or the odds ratios. Okay, and just make sure you use the right two groups. Okay, for example, if we look at the third equation, so that's between the fish and the invertebrate. Okay, so what does that mean? Let's look at the coefficient. So that means by one, oh, And by the way, the length is using the unit meters. It is using the meter as the unit. Okay, so by 1 meter increase in the length, okay, and the odds, the estimated odds that the primary food change is fish, because the fish is category 1, rather than the invertebrate, that's category 2, is increased by what? 9.5 times. Why it's 9.5 times? Because the exponential of 2.355 is what? Is 10.5, right? So that's why it's increased by 9.5. So it's 10.5 times, that means increased by 9, right? So that's how we can interpret the results. And we can do the same thing for the other two. Okay, but here you can see the larger the alligator, the more, the higher chance that they will choose, they will eat the fish as their primary food choice. So smaller alligators tends to eat the invertebrates. Invertebrates are those insects, worms, crabs, so these small things. Okay, but the larger alligator tends to eat fish. And what about the others? Right? So we can see in a minute. Okay, so others, yeah, we will see that in the next slides. Let's talk about this one first. So we can also test the X, the length is useful or not in terms of predicting the primary food choice. In other words, if it's useless, if the size of the alligator is irrelevant to the primary food choice, then the beta 1, beta 2 will be equals to what? Will be equals to 0. Is that right? So to do this test, we are essentially testing if the primary food choice is independent of the alligator size. Okay? And we can do it as a likelihood ratio test, right? So how can we do the likelihood ratio test? We can do it as first we fit a no model. A no model that assumes it is irrelevant, right? So the size is irrelevant to the primary food choice. Then that will be the fit 0, is the VGLM, the Y tilde 1. So in the R, if you have the Y tilde 1 without any X here, what does that mean? That is an intercept only model. So that is the model. If you write in this way, in R, it will know that, okay, you only want to fit the Y with intercept, no other explanatory variable. Okay, so that's the intercept, and that is the model exactly with the beta 1, beta 2 equals to 0, right? So family is still multinomial, and you can see, then we can do the LR test. That's the likelihood ratio test function to test the fit and the fit 0. And here I should write it in the fit 0 and the fit. Okay, usually we put the reduced model, the simple model first, and the complicated model second. So that's why you so anyway, so the difference is 2.6. The difference for the degrees of freedom is 2, and the test statistic is 16.8, and the p-value is highly significant. So that means what? So that means by adding the length information, the model will be is significantly improved, significantly different from just the intercept only. So that means the length of the alligator is useful to predict the primary food choice for the alligator. Okay, so that's how we can test the predictor is useful or not. Okay, so through the likelihood ratio test. Okay, so now let's see, we can also estimate the probabilities just as what we did in the logistic regressions, right? So remember for the logistic regressions, if we have the logistic regression models, how do we estimate the probability? Remember? So the probability of having y equals to 1 will be what? Will be 1 plus what? Exponential of alpha plus beta x. Is that right? And that's the denominator. Numerator is what? Exponential of alpha plus beta x. That's for predicting, for estimating the y equals to 1. What about the probability of y equals to 0 in the logistic regression? That will be 1, same as the denominator, 1 plus exponential of alpha plus beta x. Is that right? What's the numerator? Numerator is just 1. That's for the logistic regression. Is that right? And similarly here, for the baseline category logit model, the response probability is equals to this for j equals to 1 through c. Now this time I have the c here. Why? Because if it's 1 through c minus 1, these are all fine. But when it's c, remember what is alpha c and what is beta c? They are both equals to what? Equals to 0. So for the baseline group, pi c, the probability is what? The numerator becomes to 0. So e to the exponential of 0, that's 1, just like here. Okay? What is this? Okay. Okay. So so for the alligator food example, so let's see the estimated probability for the outcomes is, so the type 1 is fish. So the probability for an alligator choose fish as the primary food choice is this one, right? So the numerator is this, exponential of 1.618 minus 0.11x. What is that? That is the equation for the log odds between the pi 1 and the pi 3, right? So that's the, okay? So that's for the estimating the fish. So for the denominator is 1 plus this and this. I use different colors. The red one is the log odds for the fish against the baseline group. And the blue one is log odds model for the invertebrate against the baseline group, right? So what about 1? 1 is the baseline group. What is the baseline group? It's the group, it's the category 3. That's the others. Is that right? Yeah. Why it's 1? Because for the baseline group, this all equals to 0. So e to the 0, that's 1. Okay? So that's why we have 1 here. So that's for the pi 1 hat. And this is for the pi 2 hat. And for the pi 3 hat, that's the baseline group. We have the same denominator, but the numerator is 1. Okay? For the type 2 of, for the invertebrate, that's the this one as the numerator. Okay, so that's how we estimate the response probabilities. Okay, so we can also use the predict function in the R to do the prediction. So here we have the fitted model, fit, that's the model object for the baseline category Logit model, right? And now we have a new data set. That's the data frame for X equals to what? 1.24 meters, 2.13 meters, and 3.89 meters. So what are these three numbers come from? So the first one is the minimum length in the data set that we have. The second one, 2.13, that's the average length for the alligators in the data set. And 3.89, that's the maximum length of the alligator in the data set. So we can do the prediction. So for the minimum length, this shows the probability of choosing the fish. F is fish, I is invertebrate, and O is others for the minimum length. And the second row is the average length. And the third row is the maximum length. So I use the red color to highlight it, the food choice that has the maximum probability, estimated probability for the three different lengths. So you can see when we have a minimum length. So when the alligators are small, the invertebrate is the dominant primary food choice, right? But when the alligator grows larger, like the average size or the maximum size, you can see now the fish becomes the dominant food choice. Okay, now back to the question, what about the others? So you can see the probability for having the others as the primary food choice is increasing. However, if you look at the size, like when they are small, only 5% chance. But when they grow older, it's 15% chance. And when it's maximum, it's 23%. So you can see that when they grow older, the chance of choosing the others increases. But compared to the fish and invertebrates, others is like just like a snack for them. So the chance of choosing the others as the primary food choice is relatively small. So when they are small, they dominated by the invertebrate. When they're older, the food is dominant. Fish is the dominant food choice. So that's the interpretations based on the probabilities, and this shows the estimated probability curves. So here we only have three numbers: minimum, mean, and the maximum, right? But we can also predict the probability in very fine grain, right? And then we can connect those points for the estimated probabilities. So you can see that when the length of the alligator is small, invertebrate is dominant. Then the fish goes up when the size increases. And like here, close to 1.8, that's the point that they have some equal chance of choosing the invertebrate and the fish. Okay, but when they grow larger and larger, fish becomes dominant. But for the others, it increasing, but the size compared to the fish and invertebrate, it never becomes a dominant class. Okay. Any questions about this example? Okay. Now, for this one is checking the multinomial model goodness of fit. So to compare the model, we have two models. We want to compare these two models, like the one that we did here. We can see if the X is useful in predicting, if the length of the alligator is useful to predict the primary food choice. We can compare two models. Okay, so using the likelihood ratio test. But the goodness of fit test, as I said before, is a different purpose test. This is a test that we can use to see if the model fits the data adequately or not. So you can see the difference between the likelihood ratio test for comparing two models and this goodness of fit test for just checking if the model fits the data adequately or not. Okay, so for the goodness of fit test, we not comparing two models. We're just comparing the model fitted value with what we observed from the data. Okay, so the purposes are different. With not too sparse group data format, and as I said, the goodness of fit test is useful for mainly the group data format. Okay, if we have some X which is continuous, okay, like here, then we can not really use the goodness of fit test. Okay, but we can do the goodness of fit test like here. We can still do the goodness of fit test if we can categorize the X into just a few groups. Let's say, suppose we can categorize the length of the alligator size into three groups: small size, medium size, or large size. Then that becomes a grouped data format. Okay, so that's one way we can change the continuous predictors to categorical. But let's say if we have a group data format, then we can use the goodness of fit test. But the condition is that because the goodness of fit test is using the chi-square approximation, the test statistic. So this test statistics is approximately follows a normal a chi-square distribution, and that approximation is based on the cell counts for most of the cells should be no less than 5. So that can make the approximation is good. But if we have lots of sparse cells, most of sparse have the cell count is less than 5, then we cannot do that. Okay, and we can also do the likelihood ratio test to compare the two models, as I said before. Okay, so let's see an example. So this example is from general social survey data. So the response is belief in life after death. Okay, with categories is yes, undecided, and no. Okay, and for the explanatory variable, we have the gender. Okay, that's the X1. We set the 1 as for the male, 0 for the female. So female as a baseline. And X2 is race. Okay, and use the 1 for the white, 0 for the black as a baseline group. So this is the data set. So here, yes, undecided, no. Of course, we don't see a very clear ordering relationship, right? So, but sometimes we can put it as an order. But here, we don't see such clear patterns. So we just we can use treat the response as unordered. Okay, so here we set the no as the baseline group. That's the category 3. Category 1 is yes, 2 is undecided. Okay, so the model here we have is this one. So the alpha j from 1 and 2. Okay, 1 is for the yes group, 2 is for the undecided. Okay, so that's the intercept. Beta J G, so that's for the gender effects. Okay, so beta J R, that's for the race effect. So you can see this is a group data format, right? We can show the data sets through the tables. Okay, and this data set is available here. Still, we use the VGM package using the VGOM functions, and you can see the summary of the models. So here we just use the additive models, gender and race as additive effects. Okay, so you can see we have the 2 intercept, we have 2 betas for the gender and 2 betas for the race. Why we have 2 for gender and race and 2 intercept? Because we have 3 class for the response, and we modeled the log odds for the group for the category 1, yes against the no, for the undecided against the no, for these 2. So that's why we have 2 intercept, 2 gender, and 2 race. Okay, so the parameter beta represents the log odds. I'm sorry, log odds ratios. Yeah. So here, with the baseline categories. Okay, so here, let's say for the gender effect. Okay, so for how do we interpret, let's say, this number? That's the gender for the male, and the one means what? One means, so that's for the j equals to 1, and that's the yes. So we model the log odds between the what? Yes and the no, right? Yes is the j is 1, no is the baseline. Okay, so that's the gender male 1. For the gender male 2, that's the model the undecided to the no. Okay, so how do we interpret this one? This is, we can interpret as for the males, the estimated odds of the response yes, that's the group, that's the category 1 for the response, right? Rather than no, that's the baseline group. On the life after death are exponential of this beta, which is 0.66 times for those for the females. So in other words, males tends to not believing there's a life after death compared to the females. And odds of that for the males is only 0.66, 66%, like a 2/3%, or 2/3 compared to the females. Okay, so that's how we interpret this beta. And we can do this similarly for the, like this one. But the only difference is what? Only difference now this time is not yes against no. It's undecided against no. Okay? And similarly, we can interpret the race in the same way. Okay? So, like here, for the whites, the estimated odds of response yes rather than no are 1.4 times than for black, adjusting for the gender. Okay, so I forgot to mention adjusting for the race here. So it has to, because we have more than 2 predictors, or more than 1 predictors. So when we interpret the beta for one variable, we always need to given the other variable fixed. So that's for adjusting for the other variable. Okay, so that means white people tends to believe there's a life after death. compared to the black. Okay, females tends to believe there's a life after death compared to the males. Okay, so for the group data, we can test the goodness of fit using the deviance, right? So here we have the residual deviance is 0.85. Okay, so how to get the deviance? You can just use the deviance function. Okay, so let's see. Uh, we can also see it from here. The deviance is 0.85, right? On 2 degrees of freedom. Okay, so that's for the fit. So we have 0.85. Degrees of freedom is 2. So the model, if we look at the chi-square table, with degrees of freedom is 2, you can see the p-value is 0.65. So that means what? That means this model include the main effects for the gender and the race, fits the data, fits this table adequately well. No big difference, no significant difference between these observed counts and the fitted values from this model. Okay, so that's for the this model, and also we can test. Like here we have the gender and race, right? We want to see, let's say, if the gender is significant or not, right? Because here you can see for the word test p-value for the gender, one of them is significant, but the other one is not. What does that mean? That means for comparing the yes and the no, there's a significant difference between female and male. Is that right? In terms of the log odds. But for comparing the undecided to the no, the female and male has no significant difference. You see that? That's from the word test. But can we test? Oh, okay. Uh, let's just close here. So if we want to just test gender as a group, if overall gender has a significant impact or not, then we should do it as a likelihood ratio test, right? So what we can do is we can fit a different model, fit 2. That's a different model, but this time we only include the race. We don't include the gender. Okay, so there's no gender here, and you can see, then we can see the deviance is 8.04. Okay, so that's the deviance for only include the race, not gender. But for the including both gender and race, that's 0.85. So then we can do the like ratio test between the fit, which is including the race and gender, and the fit 2, that's including only the race. And you can see the degree of freedom is 2. Why? Because comparing these two models, the number of additional parameters included in this model is what? Is 2 parameters. That's the gender male 1, gender male 2. Is that right? Okay, so that's why comparing these two models, we have the degree of freedom is 2. And what about the test statistic for the, let's see, uh, for the test statistic, yeah, we have the chi-square is this one. Let me see, difference. Uh, that's the Yeah, that's the, let me see, this is the, okay. Yeah, that's the, uh, okay, I see. So this is the, how do we get this? So this is the, to calculate it, it's the minus 2 log likelihood from the fit 2 minus the log likelihood from the fit. Okay, so that's how we get this. In other words, this is the first one is negative 19.7, and this one is negative 23.3. You do the difference between these two and multiply it by, uh, I'm sorry, there's no negative, it's plus. Okay, 2 times that. So that is the test statistics. And then you can do the chi-square test with degree of freedom is 2, and the p-value is this. So that means there is a significant difference between these two models. Okay, so we can tell that, so that's why we can say the gender plays a significant effect to predict the belief in afterlife. Okay, so that's how we compare the models. Okay, so the next one we will talk about is the cumulative Logit model for the ordinal response. So that is the case that's when we have an ordering relationships among the categories for the response. So in that case, we can use this model. It's not the baseline, it's the cumulative Logit model. Okay, so why it's called cumulative? Cumulative means that instead of we have setting a baseline group and compare other group with the baseline, we estimate the logit for the y is no greater than class level J. Okay, so here we model the y from 1 through C categories. And of course, there's an order, right? So here we have 1, 2, 1, category 1 is the lowest level. Category 2 is the second lowest. Okay, and category C is the highest level. Okay, so then we can have the probability of having the y is no greater than 1. Of course, it's less than or equals to the probability of y is no greater than 2, and so on to the probability of y is no greater than c. And that one is equals to what? 1. Is that right? Because c is the number of categories for the response. And that includes all the possible cases. So that's 1. Okay? So the model for the cumulative, by its name, you can see it's cumulative logit. Okay, so what is cumulative logit? It's logit of the probability of less than or equals to J. And that is the log of the probability of less than or equals to J over 1 minus the probability of y is less than or equals to J. So that's the log odds for y is no greater than J. Okay, and you may ask, if we do that, how do we estimate each category's probability? Yes, we can do that. You will see that in a minute, okay? But this is the cumulative Logit model, okay? And why we need to use that? because this model take advantage of the ordering information in the response. Now we can put the orders, right? And also this model, how many parameters do we have in this model? You will see that in a minute. So here the parameters is fewer, okay? So compare to the baseline category Logit models. This model uses fewer parameters. That means the model is simpler. And the simpler means what? Simpler means potentially we can have a higher power to identify the effects from the X. And also that means simple model, we can have a easy to interpretation, a better interpretabilities for the models compared to the baseline category Logit model. Okay, so that's the motivation for using the cumulative Logit model. But this model, as I said, is only for the ordinal response. Okay, so for the cumulative Logit model, we have different types, but the simplest type is the proportional odds model. So the full name for this model is the proportional odds cumulative Logit model. Okay, so what is the proportional odds cumulative Logit model? So here we model the cumulative Logit. So that's the cumulative Logit with the proportional odds. That's the proportional odds. Okay, so why this is proportional odds? Because you can see here, the J is ranged from 1 through C minus 1. Is that right? And why is C minus 1, not C? Because if it's C, if we allow J equals to C, what will happen? This one becomes to what? This one is 1, right? So this is a constant. For a constant, Logit doesn't make sense for the constant equals to 1. Because what is Logit? That's the log odds between 1 against what? 0 here. Because that's 1 minus 1, that's 0. So this is undefined. So that's why it only ranges from J from 1 through C minus. Okay, and we would see how to get the probability of Y equals to C in a minute. Okay, so it's very straightforward. It's just 1 minus the case that when the J is C minus. Okay, so for this model, the only parameter that is relevant to the J is the intercept. But the slope of the X is the same. So that means what? That means the effect of the X on the log odds of the response in the category J or below is the same. So the X effect on the log odds of Y is no greater than J is the same for all types of J's, for all the J's from 1 through C minus 1. Okay, in other words, this plot shows everything. So here, let's say we have 3 classes. Okay, so this is the, and here this plot shows the beta is greater than 0. Okay, and I will tell you why in a minute. So if this is the probability for the Y no greater than 1, okay, it's this curve. Then the probability of no greater than 2 is this curve. Probability of no greater than 3 is this curve. So when the X increases, you can see the probability increases, right? So that's why I said beta is greater than 1. Okay, so these 3 curves, they all have the same what? Same shape. That's very important. Because what? Because the beta is constant. beta is the same for y is no greater than 1, y is no greater than 2, and y is no greater than 3. The only difference is alpha. Intercept is different. In other words, if we can shift this curve for the probability of y is less than or equal to 1 to the left, it will perfectly match the probability of y is no greater than 2. And if we shift it further to the left, it will perfectly match the probability of y is no greater than 3, and so on. Okay? So that's the proportional odds. Means that they all have the same shape for the curve. Okay? And the beta is the same. So beta didn't change for different values of j in the model. And how to get this one? So the difference between this and this plot is what? If you look at closely, this is the probability of what? Y is no greater than j. Is that clear? And this is the probability of y equals to j. Okay, so how do we get that? It's not difficult. So let's say if we have the probability of y less than or equals to 2, right? So we have this model. And minus the probability of y equals to or less than or equals to 1. What is that? That gives what? That gives, so if we do the subtraction, we get the probability of y equals to what? Y equals to 2. Is that right? So we can easily get that. So you may ask how to get the probability of y equals to 1. That is exactly equals to what? The probability of y less than or equals to 1. Does that make sense? Because the smallest is 1. This one is this, right? And we can do that. You may ask how to get the probability of y equals to c. That's the number of categories we have. That is equals to what? 1 minus the probability of what? Y is no greater than or equals to what? C minus 1. Is that right? We can get that, then 1 minus that, we can get that. So you can see, as long as we have this equation, we can easily find out the category probability, each category's probability. Is that right? And this is the cumulative, okay? So if we just look at the individual category probability, and that looks like this one for the proportional odds, okay? And this one, as I said, this is for the beta is greater than 0, right? So for this one is beta greater than 0, okay? But what if the beta is less than 0? What does this one looks like? If it's less than 0, it will just be like that. Okay, so you can easily find it. Okay, so since the same beta applies for each cumulative probability, this property is called proportional odds. The property says that the odds of the response below any particular category multiplied by exponential beta for each 1 unit increase in the x. Okay, so that's why we have a proportional odds. Why it's called proportional odds. Okay, let's see one example. Okay, so this is the political ideology and party affiliation example. So this data is from 2000 16 general social survey. So we have a 5-point ordinal scales for the political ideologies, ranging from the very liberal, that's the category 1, to liberal, that's category 2, and moderate, that's category 3, and conservative, that's category 4, and very conservative, that's category 5. Okay, so that's the order for the response. And here I put the order here. You can see that in this table. And we have two predictors. One is the party affiliation, 0 for the Democratic, and 1 for the Republican. And X2, that's for the gender, 0 female, 1 male. Okay, so that's this data. And we can, since we have an obvious ordinal relationship for the 5 categories in the Y, so we should use the cumulative Logit model. And especially here, we assume the proportional odds. Okay, so we have the proportional odds cumulative Logit model. So this is the fitted model. Okay, so for this fitted model, we have the alpha j, that's the intercept, will change for the j from 1 through 4. Remember, we have 5 categories, and that only from 1 through 4. Okay, and alpha j, that changes with the j's. And this is the for the party affiliation effects, and the beta is independent of the j's. And this is the effects. This is the coefficient for the gender effects, okay, which is also a constant, independent of the j's. So the estimated effects of the political party is this one, with standard error is 0.218. And you can see that it is highly significant. But for the gender effects, it's not. Okay, so here is the model results. And still, I use the VGM library. So this library is very good for those multi-category Logit models. And here, this is the data set. 1 is very liberal, 5 is very conservative. And use the VGOM. And this time, we have the party plus gender, right? The family is cumulative. Okay, and parallel equals to true. So what does that mean? So that means now this time we are not using the baseline Logit model. We are using the cumulative Logit model, and with the proportional odds structure. So that means the parallel is true, means that we have the beta doesn't change for the j's. Okay, so that's the parallel equals true means. Okay, so that's the proportional odds cumulative Logit model. Okay, so that's the model output. And from the model output, you can see for any fixed j, okay, the estimated odds for this for this coefficient, let's say it's the party affiliation for the Republicans. So that's negative 3.6. So what does that mean? That means for the estimated odds that the Republicans' response is in the liberal direction rather than the conservative direction. What does that mean? Remember the setting for the response is 1 is liberal, then 2 is slightly liberal, and 3 is moderate, then slightly conservative, and very conservative. So when we do the models, we model the logit for what? The probability of y is no greater than j. That is in the direction of what? In the liberal. Okay, so that's what it means. So the estimated odds that a Republican responds in the liberal directions rather than the conservative directions is what? Is 0.0026 times. How do we get that? That's the exponential of these coefficient, right? The estimated odds for the Democrats. And that's obvious, right? So in the other, and we can also interpret in the other directions. Now, this time, if we interpret in the other direction, what does that mean? That means now this time is the probability of y is what? Greater than or equals to j. Okay, so that is in the direction for the conservatives. So in the other direction, the estimated odds for the Republican is 37.9. That means if we do it in this ways, then the model will have the coefficient just flip the sign, So that will be the positive 3.63. So that is the exponential of that is 37.9. So that is 37.9 times the estimated odds for the demo. Okay, so that's how we interpret those coefficients. Okay, yeah, this is the last slides that we will talk about today. So this is the model expression for the cumulative probabilities. So if we want to estimate the cumulative probabilities, so that's the probability of y is less than or equals to j is equals to what? Is the exponential of that over 1 plus exponential of that. And here, the betas are here, but alpha is related to the j. So if j is 1, you should use alpha 1 here, alpha 1 here. If j is 2, you should use alpha 2 here, okay? So let's say, how do we calculate the probability of having the moderate political ideologies? So moderate, that corresponds to the y equals to 3. Is that right? So the probability of y equals to 3 can be calculated by the probability of y equals or less than 3. Is that right? Minus the probability of y is no greater than 2. And that difference gives the y equals to 3. So we can use this formula to find out this one, and also to find out this one. What's the difference between these two? The only difference is what? Alpha j here is alpha 3, and here is alpha 2. Does that make sense? So the difference is this one. Okay, so that's how we find out. And the R also can find that out. So this one shows the predicted probabilities for all 4 combinations: female Democrats, female Republican, male Democrats, male Republicans, for all 5 categories. And from this estimated probability, you can see the dominant category for the political ideology is for the Democrats are the slightly liberal. That's the dominant. For the Republicans are the slightly conservative. So you can see most of the peoples are either slightly dominant or slightly liberal and slightly conservative. Okay, so that's the interpretation. Any questions? Okay, if you don't have any question, let's stop here. And as I said, start to prepare for the exam twos, and we will talk about more details about exam twos later.